Good day, everyone. Thank you for being here today. I'm excited to present something truly special, our mini operating system simulator. Look at this interface. What we have here is a working simulation of 3 fundamental operating system components. Every time you open an app on your phone, play a game, or even watch this presentation, your operating system is doing all of these things simultaneously. Today, you'll see exactly how. Let's dive in. Part 1. CPU scheduling. Alright, imagine this scenario. You're at your computer right now. You have Spotify playing music, Chrome with 20 tabs open, Discord running. You're typing in Microsoft Word. Here's the thing. Your CPU has maybe 4, 8, or 16 cores. Right. But you're running hundreds of processes simultaneously. How does your computer decide who gets the CPU's attention and when? That's what CPU scheduling solves. See this input field here? This is where we define our processes. Let me show you what's already entered. Let me break this down piece by piece. P1 is process 1. It could be Spotify or any software. 0 means it arrives at time 0 and starts immediately when computer boots. P2 is process 2. It could be Chrome. 1 means it arrives 1 second later. 3 means it needs 3 seconds of CPU time. P3 is process 3. It could be a video rendering. 2 means it arrives at 2 seconds. 8 means it needs 8 seconds of CPU time. Why this format? Because operating systems need to know 3 things about every process. Number 1, who are you? Number 2, when did you arrive? Number 3, how long do you need? Algorithm number 1, first come, first served. This is the simplest algorithm. Whoever arrives first gets served first. It's like a queue at the DMV. No cutting allowed. Look at the output. What does this tell us? P1 runs from time 0 to 5, gets immediate service. P2 arrives at time 1, but has to wait until P1 finishes at time 5. P3 arrives at time 2, but waits even longer until time 8. Now, look at this Gantt chart. This is your visual timeline. See those colored blocks? Red block P1 runs first. Occupies CPU from 0 to 5. Teal block P2 runs second. Occupies CPU from 5 to 8. Purple block P3 runs last. Occupies CPU from 8 to 16. Algorithm number 2. Shortest job first. P1. Arrives at 0. Needs 7 seconds long job. P2. Arrives at 2. Needs 4 seconds medium. P3. Arrives at 4. Needs 1 second. P4. Arrives at 5. Needs 4 seconds. Watch what happens at time 7. When process 1 finishes, we have 3 processes waiting. Process 2 needs 4 seconds. Process 3 needs 1 second. Process 4 needs 4 seconds. Instead of just taking the next in line, SJF says, let's do the shortest job first. So process 3 1 second jumps ahead of P2 and P4, both 4 seconds. Round robin number 3. Round robin. Now, see this quantum field? I'm going to set it to 2. This is the game changer. See the pattern? They're taking turns? Like kids on a playground. P1 gets a turn. P2 gets a turn. P1 gets another turn. And so on. This is how your computer multitasks. Without round robin, your video call would freeze every time you clicked something. Part 2. Memory management. Alright, new scenario. Your computer has RAM, let's say 8 gigabytes. When you open programs, they need memory. But here's the challenge. You have fixed memory blocks, and processes need variable amounts. Look at our memory blocks. Think of these as parking spaces. Block 1. Compact car space 100. Block 2. Sedan space 200. Block 3. Truck space 300. To allocate memory, we need 2 things. Number 1. Process ID to let your computer know who needs memory. Number 2. The size. To identify how much memory needed. Why this is the format? Because the operating system needs to know which process is requesting memory, how much memory they need. Simple as that. Demonstration 1. First fit algorithm. Let's say process P1 needs memory. I will type process ID P1 in size 80. Look at the memory status. Why we are in the block 1? Because first fit algorithm says to start at the beginning and don't check the other blocks. So what is the advantage? The advantage is that we did not have to check block 1 and block 2. Now let's allocate. P2. Let's P2 in the process ID with a size of 180. Why block 2? Because block 1 already taken, so the algorithm have to skip it. The algorithm also checks if block 2 is 200, 180, and then we allocate and stop. Now all blocks full. If P4 arrives now, it gets rejected because there is no space available. Now, what happens when P1 finishes and exits? It should free up its memory, right? Beautiful. Block 1 is now available for reuse. This is critical. Without deallocation, you'd run out of memory quickly and need to restart your computer. Part 3. File system. Last component. Every file on your computer, your photos, documents, videos, lives in the file system. It's like a giant filing cabinet, and we're going to manage it. Demonstration 1. Creating files. Let's create a configuration file. Let's create a file name and add some contents. Look at the file system contents. Now let me add a few more to show you a real file system. Now look, we now have a working file system with 3 files. Demonstration 2. Reading files. Now imagine your application needs to read the configuration. How does it get that data? The file system retrieves the data and hands it to the application. Demonstration 3. The duplicate file problem. Watch what happens if I try to create a file that already exists. File systems enforce uniqueness to prevent confusion. Demonstration 4. Deleting files. Finally, let's clean up. I'll delete the user data file. The file is gone. In a real system, this would remove the file entry from the directory. So what have we learned today? This simulator shows you the actual algorithms that power every computing device you own. Your laptop uses round-robin scheduling. Your phone uses best-fit memory allocation. Your game console uses all 3 systems simultaneously. These aren't just theoretical concepts, they're the invisible machinery making modern computing possible. Remember, every time you open an app, play a game, or save a file, think about the incredible choreography happening behind the scenes. Hundreds of processes, gigabytes of memory, millions of files, all managed by these elegant algorithms.